shall continue with the design for shear. Last class we have done that vertical stirrups. This is one of the cases how we can provide that stirrup. The other one, inclined. Inclined stirrups or bars. Let us take one beam . We have that say compression members or hanging bars and tensile members, tensile reinforcement. So, the effective depth D and we have D dash from the top, that effective cover. We can have say so this is a crack, inclined one, say at an angle beta, and we are providing stirrups at an angle say alpha. This distance say SV. So, this is another crack, like that it can go, and we are providing stirrups. The distance, we are talking this one from here to here, this distance will be equal to, what about this one, this depth D minus D dash. So, we shall get D minus D dash times cot alpha for this side plus cot beta. So, how many bars? Number of effective bars in one region, we can say, because we can say this is one region, this spacing. So, n equal to, we can say cot alpha plus cot beta times D minus D dash divided by S V, the spacing of the inclined bars. So, number n. So, that means you have to provide that bars within this region, and we can get cot alpha plus cot beta, because we are getting this horizontal length. So, we can get n. So, this is the one, that number of bars. So, here also that instead of having D by S V, we are getting this formula, because we have to provide within this region. The maximum shear that can be carried by 1 bar equal to ASV, that is the stirrup, that cross sectional area, times the permissible maximum stress, and it should be vertical because it is inclined. We are taking these bars, so it should be inclined. This is inclined, so we are taking that one, that resisting that top one, which comes as times sine alpha. So ASB times 0.87 Fy times sine alpha we are getting. So this is the one maximum shear that one bar can take. So if we consider stirrup, so ASB, if it is two-legged, so we have taken care that twice. That we have taken care here in ASB. So the shear carried by n bars, say we can say that is say your Vs equal to ASV times 0.87 Fy times sine alpha for one stirrup, inclined stirrup you can say, times cot alpha plus cot beta, because already we have provided within this region d minus d dash divided by SV. So this is the one for single link inclined, and this one the number of links. So we can get Vs equal to this much. When the crack we are assuming at 45 degree, that crack line at 45 degree. So if we say crack line, this one, this is 45 degree. So beta equal to 45 degree, and let us assume d minus d dash equal to d. Let us assume d minus d dash, that is d, that is let us say approximately, because we can ignore d minus d dash, that let us assume that equal to d. So we can write down Vs equal to ASV times 0.87 Fy sine alpha times, so we can say we can say this particular one, okay, we could write down here. So sine alpha, so cosine alpha plus sine alpha times d divided by SV, and we shall get that in the clause, let me write down here, clause 40.4 B of IS 456 So we can get this clause, because always every time I should refer, we should refer this clause, where from you are getting this one. So this one you will get this Vs or VUS, which is mentioned in this code, you will get it VUS, that you will get it in clause 40.4 B of IS 456. Now let us come to few things here. That one generally we do it, say we call it that shear, that is as I said truss analogy. That is from the beginning of design, we call it, say as I said, truss analogy. The shear whatever we are taking care, that means the stirrups whatever you are providing, that one as if it is analogous to truss. So how it comes, let us find out. If we take a truss, truss means say it is made of, say generally most of the cases it is made of, say steel bars, steel sections. The bridges, whatever you will get it, say railway bridges particularly you will get, those are nothing but say truss. Even say your any shed, factory shed, those are called truss. So, what we will do, we are making two different kinds. So, this is your compression member. So, this is your compression member. If it happens, we can find out this way. Let us say it bends like this. So, if it bends like this, then what we will get? The members which will be extended, those are tensile members, and the members which will be shortened, those are compression members. You can find out from the deformation, that means as if it is like this. So, that means this truss, it is made of, say it is deformed in this fashion. So, what you can find out, the members which are extended, those will be, that means from here you can say, qualitatively you can say, okay, which members are that say tensile and which members say your compression. So, you can find out from this say deformation diagram, the members which are extended, so that one obviously it will be tensile members, the members which are shortened, those members will be compression members. Now, here these members, that one will be extended, and we shall get that we have to provide that one say tensile force, and here this is the analogous to that truss, that means we have to resist by this truss or stirrup in this case. In our concrete members, in the concrete beam, we are taking care that we are resisting that part by the stirrups. So, that is why we call it say your say truss, analogous to truss member. The other alternative also we can show, this is for vertical members, we can say vertical stirrups. Similarly, I can show you for the your say other one also, that means for the inclined one, which we can draw. So, we can draw out of that, again these members will be compression, and this member and this member will be in tension. This is again compression, this is compression. So, here we are providing that one, the truss analogous to truss. So, that here we are providing this one with that say inclined stirrups, that we can provide with the inclined stirrups. So, this is the way we generally provide. Let us come to the single bar single or group of parallel bars all bent up at the same cross section. us say, and let us say that is making certain angle, say alpha. So it may be only single bar or group of, that means if it is two-legged, so you are taking say two-legged means 2, or if it is a three-legged is a 3, so those are at the same cross section. So we can find out that VUS equal to 0.87 Fy times ASV times sin alpha, because we are taking that vertical one only. So we can consider this 0.87 Fy ASV sin alpha. This is the one for the single or group of parallel bars. So that is the one, that shear resistance that you can find out using this formula. There is one more that I should say, shear in beams of varying depth. This is a special case. So there are two cases, the bending moment increases numerically in the same direction in which the effective depth bending moment increases numerically in the same direction in which the effective depth increases. It means, let us particularly in the cantilever beam. In the cantilever beam, let us say this is your cantilever beam and we have certain say concentrated load P or say UDL. Then what about the bending moment diagram? The bending moment diagram, you will get it, if it is L, so we shall get P times L. So the bending moment increases in this direction. It is not a good practice, it's not a good practice, it's not a good practice that we shall provide the same depth. Generally we provide that maximum depth in the support, and in the free end we provide a little less, maybe say 250 or 200 millimeter, 150 millimeter depth we are providing in the free end, whereas in this side we are providing, maximum, because in the support. So what we can do this one. So this is your diagram. We are having say certain depth here and we are providing certain depth here. So what happens in this case? The bending moment increases numerically, we are talking numerically, in the same, because whether you are talking positive or negative, we are not talking that, so it is increasing here. So bending moment increases numerically in the same direction in which the effective depth increases. This is the case where it increases. So in that case, V will be equal to VW, whatever the shear force we shall get at that particular cross section, minus M by D effective depth times tan beta. What about beta? Beta means this angle. So we can get this beta. So V, that modified V, that one, due to this varying depth, the shear force will be modified. Actual shear force due to this applied load at a particular cross section, we shall get certain VW, that is VW, minus m by d tan beta. So, we shall get the V for which we have to design for shear. So, this is one case. The other case obviously the other way. So, let us take the other case. So, case B. The bending moment decreases last row, please last row you please come to this side, last row you come this side. In the bending moment decreases numerically in the same direction in which the effective depth increases. So, this is the other way. So, though it is not a practical one, but anyway let me give this example, because in the cantilever case it is not the actual one. So, in this case what happens, the beta, and we shall get that M V equal to VW plus M by D tan beta. This is the case B. So, we can find out that M at this, say we are interested to find out at this section what is the value M. We know the effective depth and we also know the VW. So, we can find out the corresponding V. So, these are the two, that means we have to modify that, we have to compute that V depending on the for the varying depth. We can, yes. So, this say for example, we can use you will find out say this type of beam. In bridges also you will find out. So, this type of arch, and also we can also get it say something like this also we can get it. Sometimes we provide the reinforcement that your depth near the support we provide that more. Possibly if you see that in your hall, possibly I do not know, in few halls you will find out the beams are given in this fashion. That means near the support you will get more depth, whereas in the middle you will get the less, because it is shear dominated. It means it is shear dominated. Let us do one example. Let us say a tapered cantilever beam of 2.5 meter span width 300 millimeter. It tapers from 200 millimeter depth at the free end to 450 millimeter depth at the support. What we would like to find out, let us determine the nominal shear stress at a section 2.2 meter from the free end. So, a tapered cantilever beam, let us draw the figure. Tapered cantilever beam of 2.5 meter span, this is 2.5 meter. Width, that cross sectional width 300 millimeter, this is 200 at the free end and at the support 450. I think I have a figure. Okay, and one thing I would like to tell you, in the last class actually this was wrong, because both of them was like this. So, you should note, because that one in compression, so it should be the other way. Last class when I showed that one, it was in the other side. Okay. So, anyway, so these are the, we do not want to tell these things. Okay. So, this is your problem. So, we are interested to find out that shear force here at this section due to this varying depth. So, we are having 200 millimeter, all dimensions are in millimeter, 200 millimeter, and I have forgotten to tell you that P that applied, that is 50 kilonewton. So, if we have this one, so before going for design, what you have to do, you have to find out that V due to this change, due to this varying depth, that we have to find out. So, V equal to how much? That shear force V, that is 50 kilonewton. We are interested to find out that P equal to 50 kilonewton. What about the shear force? Shear force constant, which is nothing but 50 kilonewton. This is your shear force diagram. What about the bending moment diagram? So, we shall get, so 50 into 2.5, which comes 125 kilonewton meter. But we are interested to find out somewhere here, this is 2.2 meter. So, this one it comes as M 50 into 2.2, 110 kilonewton meter. What about D? D equal to overall depth minus clear cover minus, that say 5 by 2. Let us assume that 25 millimeter the bar we are using. So, we can get, what about D? D at this point, it will be 420. So, we shall get 420 minus 25 minus 25 by 2, which comes as 382.5 millimeter, because we can get 200 and the other side we are getting 450. So, we have to find out that D, that overall depth D that we have to find out, which is coming as 420 at that particular section. What about tan beta? 450 minus 200 by 2500 equals 0.1. So, we know tan beta, which equals to 450 minus 200 by 250 equal to 0.1. So, this is case A, because bending moment increases as well as that effective depth also increases. In this case, the bending moment increases numerically in the same direction as the depth of the section increases. So, we shall get V equal to, so let us make it clear. So, let us say this is VW. Okay. In our case, let us say this is VW because we are using the formula. So, VW minus m by d tan beta equals 50 minus 110 times 0.1 divided by 0.3825. This is the d, that is we are converting in meter, and which comes as 21.242 kilonewton. In this case, we have applied the load P 50 kilonewton, which we can say the characteristics load. So, we have to get in limit state, we have to consider that one as a design load. So, design force, so design shear force VU equal to, if it is not mentioned anything wind load or earthquake load, we shall take multiply with 1.5 times 21.242, which equals 31.863 kilonewton. So, this is your the design shear force VU, which equal to 31.863 kilonewton. So, what about nominal shear stress? The nominal shear stress tau V equal to VU by BD equal to 31.863 into 10 to the power 3 divided by 300, that is the width, times 382.5, which comes as 0.2776 Newton per square millimeter. So, this is your that shear stress which is asked to find out in this problem. That tau V is not simply the whatever the shear force, so we have to modify due to varying depth, and then we can do our calculation. So, that means tau V and then tau C, all those things, then again we can continue whatever we have done in the last class. So, this is the one we shall do it for that to find out the nominal shear stress. Okay. Let us go for one more problem, and that let me explain on this problem that what we would like to do it. Let us do it in total, that flexure as well as a bending. Let us take that these are say two what is called that brick walls. This is say two brick walls, and over that we are keeping our say beams, that these two walls will support beams, the series of beams. So these are say different beams, but what I am telling that we shall not construct in this fashion just to give you that how we are going to do it, but in actual case that you are shuttering other things, everything we shall do it, it will be integral, and so over that the slab will come. So we cannot see the beam, but that is not the case. Our case is that we shall take this beam as well as the slab we shall cast integrally, so that we shall get that T section, that we can design it as a T beam. So we shall, so that we can design it as a T beam. So what we have to find out in this case, if we take and we are having flange, so it has a particular spacing, we have a spacing, and so let us take one problem that having depth, that having say flexure as well as a shear, we shall take care. So let us write down the problem first. A series of beams placed at 3 meter are supported on masonry walls. The slab thickness is 125 millimeter and rib below the slab ribs below the slab are 250 millimeter wide. The depth of the wave, let us consider, is say 250 millimeter. We are taking that, we are assuming, if it is not then we shall change it, okay, but we are taking that say 250 millimeter. Provide tensile reinforcement and let us say also design for shear. So the beam has two parts, one is that it has to resist flexure and it has to resist shear. So we are taking that this problem as a total, and if we consider, so we have this rib or web, that width that is 250 and depth also we are taking say 250. The thickness of this is the part of the slab, this is the part of the slab that we are taking, and that one here 125 millimeter depth. We have to find out the overall, that your say width of the flange also, and that we shall get it from the, we shall find out from the your that IS 456. So if we say a series of beams, that is the one, the series of beams that if we go to the previous one, so series of beams placed at 3 meter center to center, that means each of them having spacing say 3 meter, are supported on masonry walls. These are the two masonry walls. We can take say 250 millimeter. The masonry wall, let us say width of masonry wall So, we can take this, the slab thickness that is 125 millimeter, ribs below the slab that is width 250 millimeter, and depth that is 250 millimeter. We have to provide reinforcement, tensile reinforcement we are talking, because the other part, that one say you will be just only where we shall put hanger bars. So, tensile reinforcement, and mainly that one in the support, because we can take this beam as a simply supported one. We can take this beam as a simply supported one, because it is just simply, it is simply supported over the masonry walls. It is not, there is no moment here, there is no moment developed. But when we shall take care, say your that columns, that time that moment will be developed. So, for frame structures, the moment will be developed in the at the supports. But here in this case, that you will have that your say only simply supported. If it happens that one side column and one side say your masonry, then what will happen? Then it will be, you have to take care as I say propped cantilever. Okay. So, here first thing we have to find out, let us take that what about the load. So, number 1, loading. Dead load. So, we have 125 millimeter thick slab which comes as 0.125 into 25. So, 25 kilonewton per meter cube, that is the concrete, that specific weight we are taking, say your the 25 kilonewton per meter cube. So, 0.125 into 25, which comes as 3.125 kilonewton per meter square. We are providing, please note, 3.125 kilonewton per square meter. Number 2, 6 millimeter thick ceiling plaster. That means at the bottom of the slab, we are providing plaster at the bottom of the slab, and that is 6 millimeter thick. So, what you can see from the bottom, that we are providing the 6 millimeter thick ceiling plaster, and that one will be 0.006 times, here we shall not take 25, instead we shall take 24, because we are taking this one RCC reinforced, and here it is plain. So, plaster, which comes as 0.144 kilonewton per square meter. Number 3, let us provide 30 millimeter thick floor finish. 30 millimeter thick floor finish, that means at the top we are providing the 30 millimeter thick floor finish. So, which comes as 0.03 times 24 equals 0.72 kilonewton per meter square. So, dead load equals 3.989 kilonewton per square meter. So, dead load 3.989 kilonewton per square meter. Let us say that live load, that is say 4.4 kilonewton per square meter, 400 kg per square meter. Let us say that we are having say live load 400 kg per square meter. Yes. So, generally depending on the situation, I have assumed this 400 kg per square meter, but for a specific purpose, that particular building, what for that one say is made. So, on the basis of that, you have to assume that you have to get that value. So, you will get in IS code 875, that which I have told in the very first class. So 875 is the code for loading. So if it is residential building, then you are having one particular load. If it is say your public building, then you have another load. Auditorium, you have another load. Balcony, you will find out in the room you will get say your load, whatever load you will get it, whereas in the balcony, because it may be crowded, so that's why we increase the load. Staircase also, similarly the staircase, say if you take say 250 kg per square meter, that is in the room load in the room, whereas you will get that once in the balcony, say it may come say 300 kg per square meter. Similarly in the staircase, because that also may be crowded, so that's why that one also comes a little more. So different cases that you will get different load. On the basis of that, you have to calculate that load. So when we shall do one full problem, one building, that time we shall take care of that one, that what we have to do and how to analyze all those things we shall do it. Okay. So let us assume here 4 kilonewton, that means say 400 kg per square meter, that is the one say live load. So we have dead load and the live load. So number 2, what about the load on beam? Let us say dead load for slab. So individual beam, we are taking say one middle one. What we can do, you can take this beam, this end beam, the other end beam, the other side, those two end beams you can design it separately, because it will have less load compared to the inner say all these beams, this one, all of them, intermediate one, you will have the more load, and because you are getting the load, slab load from both sides. So dead load of the slab as well as live load, so that you are getting, so you will get from both sides, whereas this beam and the other end, this beam, it will have that half of the load. So you can design it separately, that means you can design it as a L beam also. But anyway, here we are taking say one any inner beams we are taking. So dead load for slabs, how much it will be? We have got 3.989, that is we can say 3.989. So 3.989 we can say, so this is the square, that means 1 meter by 1 meter. So like that it is going. When you talk say your beam, it should be per meter, that UDL whatever it is per meter. So whatever load we have got, that is say your 3.989 or 4 kilonewton per square meter. So along this length you will get, and what about this distance? So half of this, that is equal to 3 meter, isn't it? This one 3 meter, because that spacing of beams. So we can find out that per unit length it will be 3.989 times 3, which comes as 11.967 kilonewton per meter. So our load along this length you are getting, that is along this length you are getting, so multiplied by this width, so I shall get 11.967 kilonewton per meter. Similarly for the live load, okay, but before that I have already assumed, already given of course, that rib depth. Last beam it will be only this side only, half of that, means 1.5, and if there is no overhang, that means if it ends, the slab ends at the here itself, there is no overhang, if we assume, then it will be just multiplied 1.5. But if it happens that something say 0.3 meter this side also, then that also you have to take. That is 1.5 plus 0.3. But anyway, in general we can say half of that. So rib depth, say let us say 250 millimeter. Okay. And so we can get, and let us say 5% extra. So 1.05 times 0.25 times 0.25 times 25 equals 1.64065 kilonewton per meter. I have taken 5% extra for finishing other thing we have taken. So we can get 13.60765 kilonewton per meter. Total live load (4 into 3) the similar fashion, which comes as 12 kilonewton per meter. So this is, so we are getting that, say for dead load we are getting this much, and for live load we are getting this much. So W DL 13.60765 kilonewton per meter, and W live load 12 kilonewton per meter. I think we have to stop here. We shall continue the same problem in the next class. Okay. So